Today, we are going to talk about a method of encryption that is nearly unbreakable. This method is called the RSA encryption. Imagine you are trying to send a secret message to your friend or ally, but someone such as your adversary might want to intercept it. RSA encryption keeps data and transactions secure. It is used in online banking, shopping, and private messaging to protect sensitive information. Without encryption, identity thieves could steal your credit card details, or enemies could intercept classified communications. This would compromise the security of a nation. What is encryption? Encryption turns a readable message, which we call plain text, into gibberish or the ciphertext. It is like locking a message in a box that only the recipient with the key can open. Let's go over a brief history of encryption. Throughout history, people have designed different methods to encrypt messages. One method stands out as nearly unbreakable, the RSA encryption. But how does it work? Consider this number. I'm not even going to attempt reading it, but it's a pretty large number which happens to be the product of two prime numbers. RSA encryption works because factoring numbers like this is extremely difficult. To understand the magic of RSA, we need a short lesson in modular arithmetic. So what is modular arithmetic? Modulo, or mod, gives the remainder when one whole number is divided by another. For example, 7 mod 3 is 1 because when 7 is divided by 3, the quotient is 2 with a remainder of 1. Or in 10 mod 4, when 10 is divided by 4, the quotient is 2 with a remainder of 2. The reason that modular arithmetic matters for RSA is because it ensures that the calculations remain within a predictable range, making it a key component of the RSA encryption. The magic of RSA depends on the public and private keys. First, pick two very large numbers, P and Q. To keep calculations simple, we choose 3 for P and 11 for Q. Multiply them to get what we call n of 33. Before proceeding to the next step, we first must understand phi of n, which is also known as the Euler's totient function. This function happens to be the product of 1 less than P and 1 less than Q. For our example, where n is 33, phi of n is 3 minus 1 times 11 minus 1, which produces 20. Now we can go ahead and look at the second step in the process. This is where E, the public key, which is called the exponent for the encryption, is chosen. E can be as small as 3 for computational efficiency. It also works well with the chosen n and phi of n. In this process, D, which is the private key exponent, is calculated by the receiver. Both E and D satisfy the equation E times D equals 1 mod phi of n. Let's demonstrate how this works. If E is 3 and D is 7 with phi of n of 20, we get 3 times 7, which is 21. 21 mod 20 is 1, as suggested by the formula. Now, we can go ahead and move on to the encryption step. Let's say Alice wants to encrypt a simple message m of 5 for whatever reason. The formula for the encryption is m to the power of e mod n. So 5 to the exponent 3 mod 33 is 125 mod 33. This results in the ciphered value of 26. We call this output C for ciphered message. Now let's say Alice has sent the message of 26 to Bob. It is Bob's job to decrypt the message. He uses his private key D and the formula C to the exponent of d mod n to retrieve the message m. The calculation is 26 to the power of 7 mod 33. 26 to the power of 7 divided by 33 results in the remainder of 5. Now Bob knows that Alice's message was 5. Isn't that cool? So why does RSA encryption work? Remember, the security of RSA relies on the computational difficulty of factoring n and the relationship between the keys E, D, and Euler's totient function. The RSA cipher system has numerous applications in real life. This includes securing websites. RSA ensures data sent to websites is secure. Public keys encrypt data as passwords do. Private keys decrypted on the recipient server's end. Another application is crypto security. RSA secures digital wallets and transactions. Private keys sign transactions, proving ownership. Did you know sending Bitcoin requires signing with a private key to verify the transactions? RSA plays a crucial role in securing email and text messages. RSA ensures authenticity with digital signatures. Now you understand why prime numbers are precious. In our example, we used small primes P and Q to produce n. In application, these numbers consist of hundreds of digits. The largest prime number discovered recently has 24,862,048 digits. If written down, this number would occupy 8,000 to 1,000 pages. To hack and break the RSA encryption, it would take the fastest supercomputer and astronomical amount of time to factorize the product of two such primes. An adversary attempting to decipher your RSA encrypted message would not have enough time to factorize n and hack the message before it becomes irrelevant.